Hi, so welcome to Lecture 7 of Algorithms. Today we're going to be talking about some kind of simple mathematical problems that we can solve with algorithms. And we'll basically use these simple problems to prompt some of the questions we'll be asking going forward. So in particular, we'll ask, how do you go from an algorithm, a description of an algorithm, either logically or in pseudocode? How do you go from that to an actual analysis of its time complexity? And then we'll ask some really straightforward, really simple questions about algorithm optimization. I want to get a little bit of practice, a little bit of comfort in actually, doing a little bit of analysis before we launch into the more sophisticated algorithms that we'll start with in the next set of videos. So let's think about, and by the way, the textbook has a whole chapter on brute force algorithms. I encourage you to read the chapter. You may not need to read it in incredible depth, but it's kind of a nice sort of catch-all chapter for a bunch of concepts that are useful to know about. I've already talked a little bit about exhaustive search concepts in the last set of videos, but it's a useful chapter just in terms of getting your feet wet with algorithms. So if you find yourself feeling like you're out of your depth with the analysis that comes in future lectures, do spend some time specifically in the brute force algorithms chapter, because what the problems they look at are quite simple. The algorithms they look at are not particularly complex. But they can help you build some comfort in developing your intuition, developing your mathematical chops moving forward. Okay, so let's think about some simple mathematical things that we can do. And so one simple thing is evaluating a polynomial. So let's think about an algorithm for polynomial evaluation. So we've already talked about polynomials a little bit in the context of time complexity, but I'll just remind you, a polynomial is a function that's defined like this. So let's say p is a polynomial. So it's a function of x. So it's defined as the following. It's defined as the sum from I equals 0 to n of I times x to the power of I. So I can write this out. I can write down all of the terms of this sum, and it looks like this. And I'll start with the high powers, and I'll work my way down to the low powers. So it's an, which is just a number. Oh, and I should say ai is a real number for all I. Okay. So each of these a's is just a number that's multiplied by some power of x. X raised to some power. So an times x to the nth power plus an minus 1 times x to the n minus 1th power plus ... plus, and then I'll drop down to 2, a2 x squared plus a1 x plus a0, right? And that last thing is that's, you could also write that as a0 times x to the 0th power, and that would be a valid way of writing it. So here's a polynomial, and the question is, suppose I give you all the coefficients of a polynomial. What kind of an algorithm would you write to evaluate it? So our goal is to think about these coefficients as living in an array. So basically given a coefficient array, and x, and so x is just going to be a number that we evaluate the polynomial at, and the array is going to look like, I'll call it capital A, and it has indices from 0 up to n. So it has n plus 1 entries in it. What kind of algorithm would you like to use to evaluate this polynomial? So design an algorithm to evaluate the polynomial. Evaluate the above polynomial, where the polynomial itself is defined by the coefficients, right? It's actually defined by these a's. Well, one thing you could think about doing is you could say, hey, look, I've got the definition of the polynomial is here, an times x times dot 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 times x plus an minus 1 times x dot 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 times x. How many multiplications are there here, or how many x's are there here? Well, there's n x's multiplied onto each other. And then how many multiplications are there here? Well, there's n minus 1 x's multiplied onto each other, plus, and then all the way down, right? All the way down to plus just a0. So one really simple algorithm that would evaluate this polynomial would just look at the definition and walk left to right and perform all those multiplications and perform all those additions. All right, so let's actually write down pseudocode for that algorithm, for the algorithm that starts at the left of this expression and literally walks down the expression, accumulating the sum until it gets to the very last coefficient there and adds that in. So I'll call this BF polynomial for brute force. Call this BF polynomial 1. So its arguments are x, which is the point that we want to evaluate this polynomial at, and an array of coefficients, n. So what I'll do is I'll initialize a counter. So my total is going to be it's going to be a0. So I'll initialize my accumulator, my accumulated value here, and then I'll set up a for loop that it corresponds to each term that I'll add in, and then I'll set up another for loop that corresponds to each multiplication that I have to make inside each of these terms. So my outer loop here is going to start at 1 because I already have included term 0. So for I equals 1 to n, I'll say the term, right, this particular term will be initialized by its coefficient. So the term here in this place is going to be initialized at ai. So we'll put coefficient ai into this variable term, and then we'll set up another for loop that multiplies x's onto that term. So for j equals 1 to I multiply an x onto term. So term, and then I'll just write times equals, right? So I take term and then I multiply term by x. So times equals x. And then in the end here, once I'm done with that for loop, once I've computed everything in this term, basically computed everything in you know, say this term, then I add that term onto what I have before. So I add that onto the total. So here, still inside the for loop, I say total plus equals term. Okay, so essentially what I'm doing is I'm saying, you know, a0, right, that's what this is, plus, and then a1 times x, should probably make that a dot, times x, plus a2 times x, and so on. And the I loop is indexing here, so I is indexing here, and j is indexing within each term. So j is indexing here, and then I have another j that does that multiplication, and then I proceed. So it's worth just looking at the pseudocode and making sure that the indices line up. So on the pseudocode, I have my I going from 1 to n. Well, that corresponds to the fact that I have a going from that I have a1, a2 all the way up to an, and so I will consider exactly the correct number of coefficients, right? The correct number of terms to add onto the polynomial. And then j starts at 1 and goes up to I, and so let's just think about, for example, here in this term, when I is 2, what should j be? Well, j is gonna count exactly 2 times, and each time it counts, it'll multiply on an x, right? So j will multiply on that x, and it'll multiply on that x, right? So we've essentially just verified that the indexing in this algorithm, as written, is correct. So here's an algorithm. I think we can all agree this algorithm will evaluate the above polynomial. And the question is, what's the time complexity of this algorithm?